Let us start lecture 31, and the course is phase diagrams in single component and binary systems. And today's topic will continue our discussion on condensed solution, and we will try to measure or find out equation for the measurement of Gibbs free energy of mixing, enthalpy of mixing, entropy of mixing, and of course, finally, we will also calculate what will be the mixing volume, okay, or volume of mixing. Now, we have already found out an expression for del Gmix for the solution formation in case of binary situation, a binary system, and a couple of assumption we had. That is basically the main assumption is we are actually following ideal solution approach, and that follows a Raoultian behavior. Okay. That is the major aspect of our treatment, and we will continue with that treatment. In fact, we will start calculating isomorphous phase diagram using Raoultian behavior. Okay. And then we will switch to real systems where interaction between the atoms will be different, and that time we will have to deal with free energy for mixing differently than what we have done in case of Raoultian situation. Fine. So, today we will continue our discussion on the same topic, condensed system, measurement of Gibbs free energy of mixing, enthalpy of mixing, entropy of mixing, and volume of mixing. So, if you have gone through the lectures for the last 2-3 lectures, you must have seen that we have dealt solution, condensed solution, either liquid or solid solution, on the basis of Raoultian behavior. Fine. And that suggests that the solution behaves ideally, or ideal solution. And we have found out couple of expressions. One is if we try to measure for 1 mole of solution, for 1 mole of solution, if we see, so that time the free energy after mixing, which is either mgm, or free energy of the solution, this is for solution, is nothing but xa Ga bar plus xb Gb bar, and here we are taking A and B, these are the 2 components, and Na mole of A and Nb mole of B, they are mixed together. Okay. And the temperature as well as pressure both are constant. And whatever consideration we had for the Raoultian behavior, that is one is atomic size of A and B, same, bond energies are same. So, that means EAA equal to EBB equal to EAB. Okay. So, these are couple of major considerations, and in fact, we will see later that even we have to take our atomic structures, atomic arrangement. So, these are some of the assumptions. Fine. And here atomic, it becomes atomic structure either BCC or FCC when we try to form solid solution. we will see later. Okay. So, these are the major assumptions, and that time only Raoultian behavior would be followed. In fact, we have also should consider that rate of evaporation in case of liquid as well as rate of sublimation in case of solid to gas, and in case of liquid to gas, liquid to vapor and solid to vapor. So, these are intrinsic. Okay. Now, when we talk about solid solution, that time we will take rate of sublimation. You can prove this Raoultian behavior with respect to rate of sublimation, but in case of liquid solution we can take rate of evaporation. Now, this is the free energy of the solution. Now, before formation of solution we can take before solution formation, we can take it as X A G A naught plus X B G B naught, and remember this is also for 1 mole of, this is for also for 1 mole mixing, 1 mole of mixture. Okay. 1 mole of total quantity before mixing, okay, or that means solution or before mixing. And then we have found out that Gm solution minus G before mixing, it leads to delta G mix for 1 mole, and that equal to X A delta G A m plus X B delta G bar m b, and here X A and X B are the mole fractions of A and B in the solution. Now, if we try to look at these expressions, I am just writing those expression delta G m bar A bar equal to R T ln A A, and it can become R T ln X A if it becomes idle, as well as delta G m b equal to R T ln A b equal to R T ln X b when ideal solution is considered. Okay. So, we can get delta G mix equal to X A R T ln X A plus X B R T ln X B. So, this is the final expression we got. Now, if we try to calculate enthalpy of mixing, so let us calculate. So, we can go to next page. So, we are trying to calculate delta H mix for 1 mole solution or 1 mole solution formation. We know that Gibbs-Helmholtz equation so if we go back, you can see that when pressure and composition both are constant, so that time we can write H divided by T square. So, the same thing can be extended to delta G by T dt P and composition is shortened and it is written as C of MP comp, it can be written as del H T square. The same thing can be used here in order to find out del Hmix. So, this is finding del Hmix. Fine. So, we can write similar thing, we can extend. If we make it a kind of generic expression, let us say ith component in the solution, if we try to find, divided by T, this is the partial molar Gibbs free energy for ith component in the solution. P and composition fixed would be equal to minus Hi by T square. Similarly, we can write equal to, so we can make it like this because we are fixing pressure and composition, we can make it partial. Okay. So, dou like this, then this becomes minus Hi naught by T square. So, then we can write it as minus like this. So, it becomes, we can write this term as minus delta H bar M I. So, it is basically when the mixing is taking place from pure component I to the component I in the solution, that time what will be the change in enthalpy due to that formation, that is nothing but this, and divided by T square. Okay. So, for ideal solution, we have already seen that this difference is delta G I bar M. So, delta G bar M I equal to R T ln X I for ideal solution. So, then if we go into delta G bar M I by T, then it becomes R ln X I. So, if we take this expression, then we can write this. Now, you see R is a constant, X I is a constant because we are keeping composition constant, and of course, nothing is dependent on temperature. So, then this left hand side would be 0. So, equal to minus delta H I M bar T square equal to this. So, this gives me an expression which is equal to this. It means that the enthalpy of a component when we are mixing from pure condition to a solution at a constant pressure and temperature or at a fixed temperature and pressure, that time we do not get any enthalpy contribution. So, the enthalpy change due to the solution formation for any component is 0 or nil. So, if we try to extend it for binary situation, so we can get similar way, we can get H A bar equal to HA naught as well as HB bar equal to HB naught. So, we can write del H total for the formation of would be equal to N A H A bar plus N B H bar B minus N A H A naught minus N B H B naught. Why? Because this is coming from and total H before mixing. And we know Na and Nb are the number of moles of A and B which are mixed at a particular temperature and pressure. So, this becomes Na Ha bar minus Ha naught plus Nb Hb bar minus Hb naught. Okay. So, this is del H total. Now, if we try to find, this is basically total enthalpy due to mixing of Na and Nb moles of A and B, but if we try to find out what will be the molar enthalpy change. So, this would be total divided by Na plus Nb equal to Na plus Nb. This particular term becomes del H A m, and the second one would become fine. So, this is this quantity and this quantity, these are X A and this is X B and this is del H A m plus this is del H bar m b, and from this to this relation we see that this goes to 0, this goes to 0. So, and this term is nothing but del X mix for the formation of 1 mole solution, okay, is equal to 0. Fine. So, that is what in case of ideal solution formation we do not get any enthalpy contribution. So, in fact, if we try to write delta G mix now for 1 mole solution is nothing but delta H mix minus T delta S mix. This is a general this is basically the formula we have already learnt, and now we see that this goes to 0 for the ideal solution formation. Ideal solution. So, hence del G mix is nothing but minus T del S mix. So, from this relation in fact we can calculate del S mix, okay, we can calculate. Now, let me show how we calculate del V mix, because del S mix I will take up little later, but let us first show how we calculate del V mix. Finding del V mix. So, that means for the ideal solution formation. Fine. Now, we know that delta G equal to V dP minus S dt when composition is fixed closed system Okay. So, that time we can write this, and then if we write this one and T and composition fixed, so then we can write V, and in case of 1 mole substance we can write it to be Vm. Okay. Now, the same expression we can take it up for calculating del Vmix. Now, so we know that delta G delta P dou G dou P at constant temperature composition is equal to Vm. When we talk about molar volumes, that time it would also be M. Okay. Now, if we try to see delta G A M equal to R T ln x a and delta G M B equal to R T ln x b. So, we can actually use this particular expression here also. So, we can write composition, and this is one part, and the second part I can take this one on the other side, little away from here, delta G bar M B equal to R T ln x b. So, here I can write fine. Now, this would get me G A bar minus G A naught divided by dP T composition would be equal to, now coming back to this, R is a constant which is universal gas constant, T is the temperature which is constant because we are taking temperature constant, and X A is the composition which is also fixed, and X A does not depend on pressure. So, then this goes to 0. So, from here we can write this is nothing but V A bar minus V A naught, which is a standard state pure condition before mixing, equal to 0. So, this gives me V A bar equal to V A naught. And similarly, here also we can, if we do this treatment, we will get to know V B bar equal to V B naught. That means, before mixing and after mixing, the volume change is not there. Now, if we try to consider the solution formation, so we are talking about ideal solution formation of A B, and there are Na and Nb number of moles of A and B and that time we can write it like this, delta V total for solution is nothing but V solution formation, V total for the solution minus V total before mixing. Fine. So, this becomes Na Va bar plus Nb Vb bar, and this is Na Va naught minus Nb Vb naught. So, this becomes Na Va bar minus Va naught plus Nb Vb bar minus Vb naught. Now, this is basically for total. If we would like to find out what will be the mixing volume change. So, we can write for the 1 mole substance. So, this comes, so if we divide this one with Na and Nb, so this comes, so this would be divided by Na plus Nb, and here also Na plus Nb we can divide. So, it becomes, this is for 1 mole, 1 more solution. So, Vmix would be equal to Xa, this is nothing but delta Vm A plus Xb delta Vm B. So, this one and this one we have already proven that these two are 0. In fact, from here we get it. So, this is nothing but delta V A bar equal to 0, and from here also you can get delta V M B equal to V B bar minus B B naught equal to 0. So, we see that these two quantities are 0. So, then delta V mix equal to 0. So, that means we have a situation that volume change during solution formation at a constant temperature and pressure is basically that remains constant. Okay. So, we have seen that enthalpy change due to mixing is 0, and the volume change due to mixing is also 0. Okay. So, there will be no contribution from the volume, no contribution from the enthalpy during ideal solution formation. So, let me stop here. We will continue our discussion. In fact, we will continue our discussion on finding del S mix, okay, for the solution formation in our next lecture. Thank you.